Right now, a single artificial intelligence training cluster is, well, it's consuming enough electricity to power a small American city.
Yeah, it's honestly staggering when you look at the raw numbers.
Right. But the craziest part of that statistic isn't the total power draw. It's that a massive percentage of that power isn't actually being used to make the AI smarter.
No, not at all.
It's being completely wasted, just bleeding off as heat, trying to push data through archaic copper wires. So today we are looking at the physical meltdown of AI.
We are absolutely witnessing a forced evolution in hardware here. I mean, the industry is hitting a fundamental physics limit. We're shifting aggressively from a world governed by electrons to a world governed by photons.
Welcome to the deep dive. Today's date is May 21st, 2026. And the mission today is to look past the endless hype of AI software, past the flashy chips and GPUs, to uncover the hidden physical bottleneck that is currently constraining the future of artificial intelligence.
And that bottleneck, simply put, is light.
Exactly. To guide you through this, we have a really stacked collection of sources. We're pulling from recent tech press releases from Ayar Labs and Sivers semiconductors, plus some incredible deep dive Substack newsletters.
Yeah, the YIAZOU and archetype capital pieces specifically.
Right. Those focus heavily on the photonics and advanced materials side. We've also got some brand new private market data from PM Insights and, some financial commentary from X. Okay, let's unpack this, because to understand where AI is going, we first have to understand why the current data center architecture is practically melting down under its own weight.
Right, and if we connect this to the bigger picture, you really have to completely discard the idea of an AI computer as like a single box sitting on a desk.
Oh yeah, it's way beyond that.
Entirely. Modern AI architectures operate as one massive distributed machine. To train the latest frontier models, you are orchestrating thousands of GPUs spread across endless racks, rows, and sometimes even entirely different buildings.
And all of those processors have to talk to each other constantly.
Constantly. They're exchanging terabytes of data in fractions of a second just to synchronize their training weights.
And historically, we've connected all those machines using copper wires, right? Just pushing electrical signals back and forth. But according to Mark Wade, the CEO of Ayar Labs, we have officially smashed into what he calls the power wall.
The power wall, yeah, that's exactly what it is.
Because using copper wires for modern AI is like trying to run a high-speed bullet train on old wooden tracks. I mean, the sheer friction and heat are just going to warp and melt the system.
That is actually a perfect analogy. The physics of that hold up beautifully, because as bandwidth demands absolutely explode to feed these massive AI models, you have to push electrons through copper at faster and faster speeds.
Which generates a ton of resistance.
Immense electrical resistance. And that resistance creates heat. Then the heat requires more power to cool, and all of this consumes electrical power that, frankly, should be going to the actual AI compute.
It's just a vicious cycle.
Exactly. Copper has basically become a parasitic drain on the system. It's limiting the AI throughput per watt, and crucially for these tech giants, per dollar.
Which explains why the smart money is moving so aggressively into optics, using light instead of electricity to move the data.
Right. The shift is happening incredibly fast.
We actually have private market data from PM Insights from just a few days ago, May 11, 2026. Lightmatter, which is a company building a 3D stacked silicon photonics engine called the Passage platform, they were trading on the secondary market at an implied valuation of $3.16 billion.
Wow.
Yeah, and then you look at Ayar Labs, who just closed a massive $500 million Series E funding round, valuing them at $3.75 billion.
And that round was led by Neuberger Berman, right? With heavy participation from Nvidia and AMD.
Yep, the big players are all in.
And they are using that massive war chest to scale high-volume production of their co-packaged optics solution, which the industry commonly refers to as CPO.
Right. And the heart of their solution is a piece of hardware called the TeraPHY optical engine. And that delivers a staggering 8 terabits per second of bandwidth directly from the chip package.
Which is insane speed. And when you look at those numbers, it becomes really clear why investors are scrambling. Co-packaged optical architectures use about 80% less energy than traditional copper interconnects.
80%? That's massive.
It is. When hyperscalers are trying to build multi-gigawatt data centers, saving 80% of your networking power budget is literally the only way the mathematics of the facility actually work.
So we know we need to replace copper cables with optical fibers. We have to move data using light. But you can't just plug a fiber optic cable into a standard silicon GPU and expect it to work, can you?
No, you can't. Silicon actually has a fatal flaw when it comes to photonics.
Because, I mean, the tech industry has spent the last 50 years mastering silicon. It's the bedrock of all computations. We even have silicon photonics now, which our YIUZU Substack source points out is phenomenal at routing and splitting light once it's inside the chip.
Right, it's a great traffic cop for light.
But the underlying issue is that silicon is fundamentally terrible at generating that light in the first place. You can't just apply an electrical current to a silicon wafer and expect it to shoot a laser beam.
Exactly. To actually create the light, we need a very specific exotic material. And according to our sources, that material is indium phosphide, or InP.
Indium phosphide?
Yes, it's a compound semiconductor, and it possesses this really critical quantum property called a direct band gap.
Okay, let's make sure we clarify that for anyone who isn't a quantum physicist.
Fair enough. Think of a direct band gap like a sheer cliff. When you push an electrical charge like an electron off this specific cliff, it falls and releases its energy purely as a particle of light, a photon.
Okay, so no energy is lost as heat.
Practically none. Silicon, on the other hand, operates more like a bumpy staircase. When an electron bounces down a silicon staircase, it loses its energy mostly as heat rather than light.
Ah, I see.
So because of that sheer cliff property, indium phosphide can convert electricity directly into coherent infrared laser light with incredible efficiency. No wasted energy, just pure telecom wavelength light.
So if the GPUs are the brain of the AI and the fiber optic cables are the nervous system, indium phosphide is the literal nerve ending.
That's a great way to look at it.
It's the microscopic spark that fires the signal across the data center. And because silicon can't generate light efficiently, modern optical systems have to take these tiny indium phosphide laser dyes and physically bond them onto the silicon chips using advanced packaging.
Right, the NNP is being permanently embedded into the heart of the hardware itself.
Which brings us to the massive physical bottleneck hitting the industry right now in 2026, because data speeds are doubling just to keep up with AI models.
Yes, the networks are currently moving from 800G optics to 1.6T optics.
And that transition requires a physical change in the hardware. An 800G transceiver typically uses 4 optical lanes to transmit data. But to hit 1.6T, you need 8 optical lanes.
Meaning every single module suddenly needs nearly double the amount of indium phosphide.
Exactly. And when you realize that a modern AI server rack holds hundreds of these modules and a data center holds thousands of racks, you are looking at millions of individual lasers required per hyperscaler every single year. It is an exponential amplification of demand.
It's mind-blowing scale.
But wait, I have to push back here. If this material is the absolute nerve ending of AI, and we know there's a huge shortage hitting right now in 2026, why can't hyperscalers like Microsoft or Meta, who have, tens of billions in cash, just throw money at the problem and build new factories tomorrow?
What's fascinating here is that infinite money cannot override the constraints of physics and time. Well, the supply chain for indium phosphide was built over decades for a much smaller, slower telecom market. You can't just snap your fingers and spin up a new semiconductor fab. The raw NNP substrates are heavily concentrated in China, while the advanced epitaxial wafer growth is incredibly concentrated in Taiwan.
We should define epitaxial growth, because that is where the real complexity lies. It isn't just like cutting a block of material.
No. Epitaxy is the process of growing crystals one atomic layer at a time in a highly specialized vacuum chamber.
One atomic layer at a time.
Yes. You're depositing highly specific atomic structures to create the exact cliff face needed for that direct band gap we just talked about.
Wow.
And the lead times, just to purchase the specialized equipment to do this, stretch 18 to 24 months. Furthermore, skilled photonics labor, the engineers who actually know how to run these machines, is incredibly scarce.
Add on top of that the geopolitical reality. I mean, China has already introduced export licensing for indium-related materials. They recognize they hold a strategic choke point over the downstream development of Western artificial intelligence.
They absolutely do.
So when AI buyers go to the market right now, they aren't negotiating for price savings. They are fighting desperately for volume allocation.
Yeah, they just want guaranteed supply at almost any cost. Because without those microscopic lasers, a $3 billion AI cluster is just a very expensive collection of cold metal.
Exactly. And moving from the raw material to the actual lasers brings us to the companies trying to control this ecosystem. Our sources point heavily toward a company called Sivers Semiconductors.
Sivers, yeah. They are a fascinating case study in how intellectual property works in this space. They are a fabulous semiconductor company out of Sweden.
Fabless meaning they don't actually own those multi-billion-dollar manufacturing plants with the vacuum chambers we just talked about.
Right. They design the technology, hold the highly valuable patents, and then contract foundries like TSMC and Win Semiconductors to physically manufacture the chips.
And Sivers holds incredibly valuable IP for continuous wave, or CW lasers, and distributed feedback, or DFB lasers.
Yes, which are the exact precision components required for co-packaged optics. But their real strategic move was helping to write the rules for how these lasers would actually be used.
Right, back in 2021.
Exactly. Sivers joined forces with major players like Intel, Arista, and Ayar Labs to form the CWWDM MSA.
Which stands for Continuous Wavelength Division Multiplexing Multi-Source Agreement. Quite the mouthful.
It really is, but it's crucial.
Because I imagine an agreement like that is purely about removing risk. If hyperscalers are spending billions to overhaul their data centers, they can't be guessing what specific wavelength of light their custom lasers are going to run on, or hoping different manufacturers' parts can actually talk to each other.
Hardware developers absolutely hate uncertainty. Before this MSA, the industry was completely fractured. By creating a standard specifically targeting 8, 16, and 32 wavelengths operating in the O-band, they built a unified, massive market.
We should explain the O-band for our listeners because it isn't just a random choice of color, is it?
Not at all. The O-band, or original band, refers to a very specific wavelengths of infrared light, right around 1260 to 1360 nanometers.
Okay.
In fiber optics, this specific band is highly prized because it experiences zero chromatic dispersion.
Meaning what, exactly?
Meaning, as the pulses of light travel through the glass fiber, they don't smear out and overlap with each other. The signal stays incredibly sharp, which is absolutely vital when you are pushing terabits of data per second.
Got it. So by standardizing around the O-band, a vendor like Sivers knows exactly what specifications to build to, and the hyperscalers know they can buy interchangeable parts from a robust supply chain.
Exactly.
And you can see this playing out in Sivers' recent partnerships. They're teaming up with POET Technologies, combining Sivers lasers with POET's optical interposer to build pluggable transceivers.
Right, with prototypes due right about now in the first half of 2026.
But they are also partnering with ONET and Enablance Technologies to develop something called an ELS, or external light source, for co-packaged optics.
And that ELS module is a critical architectural pivot for the industry.
Okay, let's unpack this, because I see a massive contradiction here in the design logic.
Why?
The entire premise of co-packaged optics, CPO, is taking all the optical elements and tightly packing them right next to the GPU on the exact same silicon package. The goal is zero distance to save power.
Right, that's the dream.
So why on earth are Sivers and ONET building an external light source module? Doesn't making it external completely defeat the whole purpose of co-packaging?
It totally sounds like an oxymoron, I agree. But this exposes a brutal thermal reality of artificial intelligence hardware. A modern GPU running an AI training workload is essentially a blistering hot space heater. It routinely runs at temperatures approaching 90 degrees Celsius.
Wow. Meanwhile, high-precision indium phosphide lasers are incredibly fragile when it comes to temperature, right?
Extremely. If you put a microscopic laser array directly next to a processor radiating that much heat, the laser will just outright fail. Or it will lose its wavelength stability.
Meaning the color of the light changes.
Exactly. The actual color of the light will drift out of the O-band, which instantly corrupts the data stream. It acts as a self-destruct mechanism if the brain and the nerve endings are too close together.
Okay, so the external light source solves this thermal death trap.
Precisely. You put the temperature-sensitive indium phosphide lasers in a separate cooler module that plugs into the front panel of the server rack.
And then you just pipe the continuous light via short fibers into the co-packaged optical engine sitting on the hot chip.
You got it. It ensures the lasers survive, and if one ever does burn out, a technician can just swap the external module rather than having to throw away a $30,000 AI processor.
That makes so much sense. You are keeping the compute engine hot and the optical nerve endings cool. It's a really elegant engineering solution to a brutal physics problem.
It really is.
Here's where it gets really interesting, though. Let's talk about the money. Because if you are listening to this and wondering how to value companies sitting on this kind of world-changing physical bottleneck, you are definitely not alone.
Oh, it is a mess out there.
Yeah, while the technological potential of these photonics companies is incredibly clear, their actual financial realities right now are messy, highly speculative, and just wildly uncertain.
The Archetype Capital Substack piece actually calls this the Photonics valuation problem. It is giving institutional investors absolute whiplash trying to model this out.
Let's look at Sivers again. According to their own investor presentations, they are sitting on a massive potential total addressable market over $2 billion by 2028 just for their laser arrays.
Right, huge potential.
But their actual real-world revenue, it's tiny. They were annualizing around $40 million right before this massive 1.6T ramp-up is supposed to start.
Which leads to a furious debate in the equity markets. You have value investors arguing that Sivers' market cap, which has fluctuated between $250 million and $400 million recently, is purely speculative for a company bringing in such little cash.
Sure.
But on the other side, growth investors argue that $500 million is incredibly cheap for a company that holds a literal IP choke point on the lasers required by heavyweights like Ayar Labs and Marvell.
I mean, investing in these photonics companies right now is like buying tickets to a concert where the band hasn't even learned to play their instruments yet.
Right.
But, and it's a big but they happen to own the only guitars in the entire world.
Exactly. You aren't valuing the company based on how much they sold yesterday. You're trying to quantify the 2027 to 2030 rollout. It's a high-stakes gamble on who controls the IP when the launch of Light finally happens.
And because the real tidal wave revenue from the 1.6T upgrade cycle doesn't begin to materialize until 2027 and 2028, traditional financial metrics tell you almost nothing. Price-to-sales ratios are meaningless when the massive sales haven't officially started.
You see this chaotic valuation across the entire sector, honestly. The Archetype piece highlights Applied Optoelectronics, ticker AAOI.
Oh, yeah.
They're relying on incredibly aggressive management projections. They're telling the market they can hit $378 million in monthly revenue by Q2 of 2027.
Monthly! That is wild.
Yeah. They are aggressively projecting that they will utterly dominate the upcoming transceiver upgrade cycle. And based on that assumption, the market has rewarded them with a massive $7 billion valuation.
Contrast that staggering valuation with a company like Soitec, which the Substack author argues is the deeply undervalued play in the space.
Right. So Soitec provides engineered substrates, essentially the foundational wafers that these advanced chips are built on.
And despite being highly critical to the supply chain, they're trading at an enterprise value to EBITDA multiple of around 7x. Let's quickly define EV to EBITDA for our listeners.
Sure.
It's enterprise value to earnings before interest, taxes, depreciation, and amortization. Basically, it's a metric that looks at what it would cost to buy the entire company, including its debt, compared to the pure cash it generates from its core operations.
And a multiple of 7x is generally considered very cheap in the tech sector, especially compared to the sky-high multiples of AI software companies.
It really creates a wildly uneven landscape for anyone trying to deploy capital. And the companies themselves are going through massive, painful growing pains as they try to scale. Look at the May 2026 press releases from Sivers.
Oh, the restatements.
Yeah, they just announced they had to restate their 2024 and 2025 financials. They're adjusting revenue allocations, writing down some inventory, and impairing capitalized development costs. They even had to delay their Q1 2026 earnings report just to get the accounting straight.
Now, restatement usually triggers panic, but the context of why they are doing it is the really important takeaway here.
Right. The press release explicitly states they're upgrading their financial reporting to align with US PCAOB standards,
Which is the Public Company Accounting Oversight Board.
Meaning they are adopting Sarbanes-Oxley level scrutiny, the strictest audit trails required by U.S. regulators, all because they are preparing for a potential dual listing on the U.S. NASDAQ.
They are actively getting their house in order for the big leagues. They know that to fund the massive scaling required to meet hyperscaler demand, they need access to the deep pools of capital in the United States markets.
So they're just undergoing the painful accounting surgery now so they can capture the 2027 rollout?
Exactly.
So to summarize this incredible deep dive, we started with the absolute physical limits of our current technology. Data centers are melting down because copper wires have hit the power wall, generating too much electrical resistance and basically choking the bandwidth of AI.
Which has forced the industry into a multi-billion-dollar pivot toward co-packaged optics, using infrared light to move data.
And we followed that light down to the atomic level to the magic material known as indium phosphide.
Thanks to its direct band gap, it is the only substance capable of efficiently generating that light at scale.
And because of highly concentrated supply chains in China and Taiwan, Coupled with equipment lead times stretching up to 2 years, indium phosphide has quietly become the physical bottleneck of the global AI boom.
Meanwhile, choke point companies holding the vital patents, like Sivers Semiconductors, are desperately partnering with the ecosystem to build external light sources, solving the thermal heat crisis of modern AI processors.
All while the financial markets suffer whiplash, trying to figure out how to value a sector that is currently making millions, but sits on the precipice of a multi-billion-dollar highway rollout.
It is a phenomenal hidden world.
It really is. So, the next time you are sitting at your desk and you type a complex prompt into an incredibly fast AI tool and you get that instant magical response, I want you to remember that it isn't just a clever software trick. Somewhere in a massive humming data center, there are millions of microscopic indium phosphide lasers firing perfectly in sync, shooting invisible light across glass threads just to answer your question.
And that leaves us with one final and perhaps deeply concerning thought to ponder.
Oh, what's that?
Well, we know that AI hyperscalers are incredibly well-funded, and they prioritize volume certainty over price. They are currently moving to lock up the entire global supply of indium phosphide lasers in massive long-term agreements.
Right.
But indium phosphide isn't just used for artificial intelligence. It is the foundational material for regular telecom and internet infrastructure around the globe.
Oh, wow.
So what happens to the rest of the world's internet upgrades? You know, the broadband fiber to your house,
Yep.
the 5G cellular towers in your city, when a handful of AI giants simply buy out the entire global supply of light.
Wow. That is, yeah. We started this dive looking for the physical bottleneck constraining AI, but AI might just become the bottleneck constraining everyone else. Thank you for joining us on this deep dive into the hidden hardware of the future. We will catch you next time.